Welcome to Cosmic Canvas, a visual voyage through the boundless expanse of the universe. From the smallest particles to the grandest galaxies, we are poised to explore the incredible tapestry of existence that surrounds us. Join us as we journey through billions of light years, unveiling wonders that defy imagination and challenge our very perception of reality. Our universe is a masterpiece awaiting discovery. For millennia, humanity has gazed upon the night sky, captivated by its silent majesty. Early civilizations mapped constellations, attributing myths and legends to the distant stars. This innate curiosity spurred the development of early observatories, primitive yet profound tools that marked the first steps in our cosmic exploration, laying the foundation for modern astronomy. The universe, as we understand it today, is a continuum of space and time that began with the Big Bang approximately 13.8 billion years ago. This monumental event initiated the expansion of space itself, creating the framework within which all matter and energy would eventually coalesce and evolve. It wasn't an explosion asterisk in asterisk space, but an expansion asterisk of asterisk space. In its infancy, the universe was an incredibly hot, dense plasma, a soup of fundamental particles. As it expanded, it cooled, allowing these particles to come together. Protons and neutrons formed first, then combined to create the nuclei of the lightest elements, hydrogen and helium. These building blocks were essential for everything that followed. Gravity, the most pervasive force in the cosmos, began to exert its influence on these early distributions of matter. Over vast stretches of time, slight irregularities in density amplified, drawing more and more hydrogen and helium into ever larger clumps. These nascent clouds were the seeds from which the first stars and galaxies would eventually emerge. The first stars, known as population III stars, were true behemoths. Composed almost entirely of hydrogen and helium, they burned incredibly hot and lived fast, short lives, fusing lighter elements into heavier ones in their cores. These stellar pioneers ignited the darkness of the early universe, ushering in the era of light. When these first stars exhausted their fuel, they met spectacular ends in colossal supernovae. These explosions were the universe's original cosmic foundries, scattering newly forged elements like carbon, oxygen, and iron across interstellar space. This process enriched the cosmos, providing the raw materials for subsequent generations of stars and planets. Now let's consider the fundamental forces that govern everything we see. The strong nuclear force binds atomic nuclei, while the weak nuclear force plays a role in radioactive decay. Electromagnetism governs light and chemical bonds, creating the intricate structures of matter, from atoms to molecules, allowing for life itself. But the most famous force, gravity, shapes the large-scale structure of the universe. It pulls stars into galaxies, galaxies into clusters, and clusters into vast superclusters. Without gravity, the universe would be a diffuse, featureless expanse, lacking the incredible cosmic structures we observe today. Our journey now takes us to stars, the celestial furnaces of the universe. Born from collapsing clouds of gas and dust, a star begins its life by igniting nuclear fusion in its core, converting hydrogen into helium. This process releases immense energy, causing the star to shine brightly for millions or billions of years. The vast majority of stars, like our Sun, spend their main sequence lives in a stable equilibrium, balancing the inward pull of gravity with the outward pressure from fusion. Their color and size depend on their mass. Massive stars are hotter and bluer, while smaller stars are cooler and redder. As a star ages, its hydrogen fuel begins to deplete. For stars like our Sun, the core contracts and heats, causing the outer layers to expand dramatically, transforming the star into a red giant. This phase can engulf nearby planets, fundamentally altering the star's surrounding system. Eventually, the outer layers of a red giant drift away, forming a beautiful, expanding shell of ionized gas known as a planetary nebula. These cosmic masterpieces are short-lived but visually stunning, glowing vividly in various colors as they are lit by the hot, exposed core of the dying star. At the heart of the planetary nebula lies a white dwarf, the dense, compact remnant of a star's core. Roughly the size of Earth, a white dwarf slowly cools over billions of years, eventually becoming a cold, dark black dwarf, which hasn't yet been observed as the universe is not old enough. More massive stars follow a different, more dramatic path. After exhausting their hydrogen, they swell into red supergiants, often hundreds or even thousands of times the radius of our Sun. These stellar titans are on the cusp of an even more explosive fate. The spectacular demise of a massive star is a supernova, a cosmic explosion so powerful it can outshine an entire galaxy for a brief period. During this event, the star's core collapses with immense force, triggering a shockwave that blasts the outer layers into space at incredible speeds. What remains after a supernova depends on the progenitor star's initial mass. For stars that were moderately massive, the collapsed core forms an incredibly dense neutron star. Here, protons and electrons are crushed together to form neutrons, packing an entire sun's mass into a sphere just miles across. If the star was exceedingly massive, the supernova's collapse transcends even the neutron star stage, leading to the formation of a black hole. These cosmic enigmas possess gravitational fields so intense that nothing, not even light, can escape once it crosses the event horizon. Our cosmic canvas extends beyond individual stars to the grand structures they inhabit, galaxies. These gargantuan collections of stars, gas, dust, and dark matter are held together by gravity. Our own Milky Way galaxy is just one of billions scattered throughout the observable universe. Galaxies come in various morphologies. Spiral galaxies, like our Milky Way, are characterized by their flattened, rotating disks and prominent spiral arms. These arms are areas of active star formation, appearing bright with young, hot blue stars. Elliptical galaxies, in contrast, are spherically or egg-shaped and contain mostly older stars, with little ongoing star formation. They range from nearly spherical to highly elongated, often found at the centers of galaxy clusters, having grown through mergers. Irregular galaxies lack a defined shape, often resulting from gravitational interactions or collisions between other galaxies. These cosmic train wrecks can trigger bursts of star formation, making them appear chaotic but vibrant. Galaxies are not static. They are constantly interacting, pulling at each other with gravity. Galactic mergers are common, leading to dramatic reorganizations, bursts of star formation, and the eventual formation of larger, often elliptical, galaxies. Our own Milky Way is on a collision course with our nearest large galactic neighbor, the Andromeda Galaxy. In about 4.5 billion years, these two colossal spirals will begin a gentle but inevitable dance, eventually merging to form a new, larger elliptical galaxy, sometimes dubbed Milkomeda. Galaxies themselves are not randomly distributed, but are organized into even larger structures. Gravitational attraction brings them together into clusters, which can contain hundreds or even thousands of galaxies, bathed in hot intergalactic gas that emits X-rays. These clusters, in turn, are part of even grander cosmic superclusters, the largest known structures in the universe. Superclusters form a vast, intricate cosmic web, with galaxies and clusters strung along filaments and separated by immense, nearly empty voids. Let's bring our focus closer to home, to our own cosmic neighborhood, the solar system. Orbiting our Sun, a relatively average yellow dwarf star, are 8 planets, numerous dwarf planets, countless asteroids and comets, all bound by the star's immense gravitational embrace. The Sun, our life-giving star, is a colossal sphere of superheated plasma. Its energy, generated through nuclear fusion in its core, provides the light and warmth essential for life on Earth. Solar flares and prominences showcase its dynamic and powerful nature. Nearest to the Sun is Mercury, a small, heavily cratered world with extreme temperature variations. Its thin exosphere is constantly being replenished by solar wind, making it a stark, airless landscape shaped by countless cosmic impacts. Venus, shrouded in thick, toxic clouds, is a planet of extreme heat and crushing atmospheric pressure, the result of a runaway greenhouse effect. Its surface, mapped by radar, reveals volcanoes and vast plains, hinting at a geologically active past. Earth, our unique blue planet, stands out as the only known world supporting abundant life. Its perfect distance from the Sun, a stable atmosphere, liquid water, and a protective magnetic field combine to create our habitable home. Mars, the red planet, is a dusty, barren world with intriguing geological features suggesting a wetter past, including ancient riverbeds and polar ice caps. The search for signs of past or present life on Mars continues to be a major focus of space exploration. Beyond Mars lie the gas giants, starting with Jupiter, the largest planet in our solar system. Its colossal size, iconic Great Red Spot, and numerous swirling cloud bands make it a mesmerizing and dynamic world. Saturn, famous for its magnificent ring system, is a breathtaking spectacle. These dazzling rings are composed of billions of icy particles, ranging from tiny dust grains to house-sized boulders, constantly orbiting the planet. Uranus, an ice giant, orbits the Sun on its side, a unique tilt likely caused by an ancient collision. Its atmosphere of hydrogen, helium, and methane gives it a distinct blue-green hue, and it boasts a faint ring system and numerous moons. Farthest of the main planets is Neptune, another ice giant, characterized by powerful winds and striking blue color due to methane in its atmosphere. It hosts dynamic storm systems, including ancient dark spots that appear and disappear. Beyond Neptune lies the Kuiper Belt, a vast donut-shaped region of icy bodies, one of which is Pluto. While reclassified as a dwarf planet, Pluto and its companions offer valuable insights into the early, cold outer reaches of our solar system. Countless asteroids, rocky remnants from the solar system's formation, primarily reside in the asteroid belt between Mars and Jupiter. These diverse celestial bodies range from mere pebbles to hundreds of kilometers across, some with their own small moons. Further out, beyond the Kuiper Belt, lies the Oort cloud, a theoretical sphere of icy objects extending to the very edge of the Sun's gravitational influence. This is believed to be the source of long-period comets, which occasionally plunge into the inner solar system. Comets, with their spectacular tails, are icy wanderers that originate from the outer reaches of our solar system. As they near the Sun, their ice sublimates, forming a glowing coma and a magnificent tail that can stretch for millions of kilometers. Our solar system is part of the Orion Arm, one of the spiral arms of the Milky Way galaxy. From our vantage point, we see billions of stars, but the full immensity of our galaxy, with its dark matter halo and central supermassive black hole, remains a subject of ongoing research. At the very heart of the Milky Way lies a supermassive black hole, Sagittarius A. While invisible itself, its immense gravity influences the orbits of stars in the galactic core, revealing its presence and colossal mass. Beyond our galaxy, across unimaginable cosmic distances, lies the observable universe, the portion of the cosmos whose light has had time to reach us. It's a sphere of billions of galaxies, each a universe of stars, nebulae, and dark matter. The expansion of the universe is a foundational concept in modern cosmology. Edwin Hubble's observations showed that galaxies are generally moving away from us, and the farther away they are, the faster they recede, a phenomenon known as Hubble's law. This expansion implies that the universe was once much smaller and denser. Extrapolating backward in time leads to the Big Bang theory, not an explosion in space, but the expansion of space itself from an infinitely dense, hot state. A crucial piece of evidence for the Big Bang is the cosmic microwave background radiation. This faint, uniform glow detected across the entire sky is the leftover heat from the very early universe, cooled and stretched by billions of years of expansion. However, the visible matter, stars, planets, gas, and dust, accounts for only about 5% of the universe's total mass energy content. The remaining 95% is composed of mysterious entities. Dark matter and dark energy. Dark matter, which makes up about 27% of the universe, does not emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred only through its gravitational effects on visible matter, holding galaxies and clusters together. Even more mysterious is dark energy, comprising roughly 68% of the universe. This enigmatic force is believed to be responsible for the accelerating expansion of the universe, pushing galaxies further apart at an ever-increasing rate. The fate of the universe ultimately depends on the interplay between dark energy and the total density of matter. Will it expand forever, eventually leading to a big freeze or heat death? Or will dark energy eventually dissipate, allowing gravity to pull everything back in a big crunch? Another fascinating cosmic phenomenon is gravitational lensing. Massive objects, like galaxy clusters, can warp spacetime, bending the light from more distant objects. This effect acts like a cosmic magnifying glass, allowing us to see incredibly remote galaxies. Quasars, incredibly luminous active galactic nuclei, are thought to be powered by supermassive black holes accreting vast amounts of matter at the centers of distant galaxies. They are among the brightest objects in the universe and serve as cosmic beacons, illuminating the early universe. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As these beams sweep across Earth, we detect them as precise, periodic pulses, making pulsars cosmic lighthouses. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that originate from outside Earth's solar system. These particles travel through space at nearly the speed of light, carrying immense energy and providing clues about violent events in the universe. Gamma-ray bursts are the most powerful explosions in the universe, releasing more energy in seconds than our sun will produce in its entire lifetime. They are associated with the collapse of massive stars or the merger of neutron stars, signifying extreme cosmic violence. The search for extraterrestrial life is one of humanity's deepest aspirations. Are we alone in this vast cosmic ocean? The discovery of exoplanets has dramatically reshaped our understanding of planetary systems beyond our own. Thousands of exoplanets have been confirmed, orbiting stars far beyond our sun. Many are gas giants like Jupiter, but a growing number of smaller, rocky planets are being found, some potentially situated within their stars' habitable zones. The habitable zone, or Goldilocks zone, is the region around a star where conditions are theoretically just right for liquid water to exist on a planet's surface. This is considered a prime indicator for potential life as we know it. Astrobiology is the interdisciplinary field dedicated to understanding the origin, evolution, distribution, and future of life in the universe. It combines astronomy, biology, chemistry, and geology to tackle fundamental questions about life's existence. The Fermi paradox grapples with the contradiction between the high probability estimations for the existence of extraterrestrial civilizations and the apparent lack of evidence or contact. Where is everyone? This question remains one of cosmology's most profound. Understanding the universe is a journey driven by human ingenuity and technological advancement. Telescopes, from optical to radio, are our eyes on the cosmos, allowing us to peer across vast distances and unravel cosmic mysteries. Ground-based observatories, often located in remote, high-altitude locations to minimize light pollution and atmospheric distortion, provide incredible insights into the universe at various wavelengths. Space telescopes, free from the distorting effects of Earth's atmosphere, offer unparalleled clarity and access to the full electromagnetic spectrum. Instruments like the Hubble Space Telescope have revolutionized our view of the cosmos. The James Webb Space Telescope, a successor to Hubble, is designed to observe the universe in infrared light, allowing it to peer through dust clouds and observe the earliest galaxies and star formation. It's a true time machine. Beyond telescopes, robotic space probes have conducted close-up studies of planets, moons, asteroids, and comets within our solar system. Missions like Voyager, Cassini, and Perseverance have vastly expanded our knowledge. Human spaceflight, though primarily confined to low Earth orbit, represents our direct presence in space. The International Space Station serves as a unique laboratory for scientific research and a testament to international collaboration. The Apollo missions, which landed humans on the Moon, represented a monumental leap in human exploration. They demonstrated our capability to transcend our planetary bounds and directly touch another celestial body. Future space exploration plans include returning humans to the Moon with the Artemis program and eventually sending crewed missions to Mars. These endeavors promise to further unlock cosmic secrets and expand humanity's reach. The development of new propulsion technologies, such as nuclear thermal propulsion or even warp drive concepts, could drastically reduce travel times to distant destinations, paving the way for interstellar travel. However, the immense distances involved in interstellar travel pose significant challenges. Even at light speed, reaching the nearest star takes years, highlighting the sheer scale of the cosmos. The concept of a multiverse, an infinite ensemble of universes, is a highly speculative but intriguing idea in theoretical physics. Each universe could have different physical laws, constants, and initial conditions. Black holes, originally theoretical constructs, are now routinely observed. They come in stellar mass varieties, remnants of supernovae, and supermassive ones found at the centers of nearly all large galaxies. The study of gravitational waves, ripples in spacetime, opened a new window to the universe. Detected by observatories like LIGO, these waves reveal cataclysmic events like black hole mergers, providing unprecedented insights into the cosmos. Our chemical elements, from the oxygen we breathe to the iron in our blood, were forged in the hearts of stars and in supernova explosions. We are quite literally stardust, intricately linked to the cosmic processes that created the universe. The cosmic calendar helps us visualize the universe's vast timeline by compressing it into a single year. The Big Bang occurs on January 1st, our solar system forms in early September, and recorded human history takes place in the last few seconds of December 31st. The concept of cosmic inflation suggests that the universe underwent an extremely rapid, exponential expansion in the first tiny fraction of a second after the Big Bang. This theory explains many observed features of the cosmos, such as its flatness and uniformity. Dark energy's nature remains one of the greatest mysteries. Is it a constant energy density of space itself, a property known as the cosmological constant, or a dynamic field that changes over time? Resolving this is key to understanding the universe's ultimate fate. The universe is dominated by plasma, an ionized gas of charged particles. This state of matter is found in stars, nebulae, and the space between galaxies, making it the most abundant form of ordinary matter in the cosmos. Superclusters, like our Laniakea supercluster, are gravitationally bound structures that span hundreds of millions of light years. They flow towards massive gravitational attractors, revealing the intricate dance of cosmic structures. The boundary of the observable universe is determined by how far light has traveled since the Big Bang. Beyond this horizon lies the unobservable universe, which may or may not be fundamentally different. Neutrinos, often called ghost particles, are fundamental particles with almost no mass and travel at nearly the speed of light. They interact very weakly with matter, allowing them to pass through stars and planets, carrying information directly from cosmic events. Cosmic dawn refers to the period roughly 200–400 million years after the Big Bang, when the first stars and galaxies ignited, bringing an end to the cosmic dark ages. Studying this era is a major goal for next-generation telescopes. Tidal forces, the differential gravitational pull exerted by one celestial body on another, are behind many cosmic phenomena. They shape galactic interactions, create ocean tides on Earth, and even tear apart small objects near massive black holes. The search for biosignatures, indicators of life such as specific atmospheric gases or organic molecules, on exoplanets is a cutting-edge field. Upcoming observations might provide the first definitive evidence of life beyond Earth. Meteor showers occur when Earth passes through the debris trail left by a comet or asteroid. Tiny particles burn up in our atmosphere, creating ephemeral streaks of light across the night sky, a beautiful reminder of our cosmic journeys. Planetary formation is a complex process where dust and gas in a protoplanetary disk around a young star gradually coalesce through accretion. Over millions of years, these tiny particles grow into planetesimals, then protoplanets, and finally full-fledged planets. The concept of a global magnetosphere, like Earth's, is crucial for life. Generated by our planet's liquid outer core, it deflects harmful solar wind and cosmic rays, protecting our atmosphere and allowing life to flourish on the surface. Solar cycles, driven by the sun's magnetic activity, influence space weather and events like solar flares and coronal mass ejections. These cycles can affect Earth's technological infrastructure, highlighting our sun's dynamic nature. The Kuiper Cliff is an unexplained drop-off in the number of objects observed beyond a certain distance in the Kuiper belt. This enigmatic boundary might hint at the existence of an undiscovered, massive planet influencing the region. The cosmic distance ladder is a series of interconnected methods used by astronomers to measure the vast distances to celestial objects. From parallax for nearby stars to supernovae for distant galaxies, each step builds upon the previous one. The study of cosmic rays, high-energy particles from space, provides clues about powerful phenomena like supernovae and active galactic nuclei. When they hit Earth's atmosphere, they produce showers of secondary particles that can be detected. Interstellar clouds, vast accumulations of gas and dust between stars, are the nurseries where new stars and planetary systems are born. Their intricate, often beautiful structures reveal the ongoing cycle of cosmic creation. The cosmic web, made of filaments and voids, is the largest structure in the universe. Galaxies cluster along these filamentary structures, driven by the large-scale distribution of dark matter, forming a complex network. Exoplanet discovery methods include the transit method, where a planet periodically dims its star's light as it passes in front, and the radial velocity method, detecting a star's wobble caused by an orbiting planet's gravitational tug. The universe's fundamental constants, such as the speed of light or the gravitational constant, seem finely tuned for the existence of life. Even slight variations could render the cosmos utterly inhospitable. The concept of wormholes, hypothetical tunnels through spacetime, offers a theoretical shortcut for interstellar travel. While fascinating, currently they remain firmly in the realm of science fiction and theoretical physics. Baryonic acoustic oscillations, or BAO, are fossilized sound waves from the early universe imprinted on the distribution of matter. They provide a standard ruler for measuring vast cosmic distances and constraining cosmological parameters. The age of the universe can be precisely determined from the expansion rate and the composition of the universe, particularly the amounts of dark matter and dark energy. This allows us to understand the timeline of cosmic evolution. The search for techno-signatures, evidence of advanced technology from extraterrestrial civilizations, includes looking for unusual radio signals, megastructures like Dyson spheres, or artificial planetary atmospheric compositions. The cosmic horizon represents the maximum distance from which light has had time to reach us since the Big Bang. It's not a physical boundary, but a limit to our current observation, expanding as the universe ages. The universe is still expanding and evolving. New stars are being born, galaxies are merging, and the fabric of spacetime itself continues to stretch. We are witnessing an ongoing cosmic drama. Our fascination with the cosmos is deeply ingrained in human culture. From ancient myths to modern science fiction, the universe inspires awe, wonder, and a profound desire to understand our place within it. Planetary defense involves identifying and mitigating potential asteroid or comet impacts that could threaten Earth. Teams around the world monitor near-Earth objects and study deflection strategies. The concept of deep time illustrates the immense periods over which cosmic and geological events unfold. Our human lifespan is but a fleeting moment on the vast cosmic calendar. The multiverse hypothesis offers intriguing possibilities for the origin of our universe's specific laws and constants. Perhaps our universe is just one of many, each with its own unique properties. The human endeavor to build ever larger and more precise telescopes reflects our insatiable curiosity. Each new generation of instruments pushes the boundaries of our vision, revealing fainter, more distant, and earlier light. Cosmic topology explores the overall shape and connectivity of the universe. Is it flat, curved like a sphere, or curved like a saddle? Current evidence suggests it is remarkably flat. The Standard Model of Particle Physics describes the fundamental forces and particles that make up all known matter in the universe. It's a cornerstone of our understanding of the universe at its most basic level. The universe's expansion isn't uniform. Local gravitational attractions cause galaxies within clusters to move towards each other, while the overall expansion of space stretches the distances between clusters. The study of exoplanetary atmospheres through techniques like transit spectroscopy allows us to search for chemical signatures that could indicate the presence of life or habitability beyond Earth. The cosmic dawn, the period when the universe transitioned from dark and neutral to illuminated and ionized, is a crucial epoch. Observations of the 21-centimeter line from hydrogen may hold the key to understanding this transition. The concept of the Great Attractor points to a massive, unseen concentration of mass that pulls our Milky Way and other galaxies in our supercluster towards it. Its exact nature remains a subject of intense scientific scrutiny. The universe is primarily empty space. Even within galaxies, the distances between stars are staggering. If the Sun were a grain of sand, the nearest star would be several kilometers away, highlighting the immense void. The universe has a beginning, and it will have an end, though the exact nature of that end is still debated. Our understanding of its history and future continues to evolve with every new discovery. Our existence is a fragile miracle born from cosmic processes. From the Big Bang to stellar fusion, the precise conditions for life emerged from a complex interplay of forces and matter. The universe challenges our perceptions of scale, time, and significance. It humbles us, reminding us how tiny we are, yet it inspires us to reach further, to know more. Every day, new discoveries from telescopes and space missions expand our cosmic canvas. We are in an exciting era of astronomical exploration, constantly rewriting the story of the cosmos. The universe teaches us about the impermanence of things, the constant cycle of birth, life, and death on a grand scale. Stars die, but their elements live on in new generations. And so, our voyage through the cosmic canvas concludes. We have merely skimmed the surface of its infinite wonders, but what we've seen reveals a universe of unimaginable beauty, power, and mystery. The journey of discovery is far from over. With every new instrument, every brilliant mind, we inch closer to understanding the grand design of the cosmos and our profound place within its endless, evolving story. Thank you for joining us on Cosmic Canvas.